Alright, so this video section is for force. If you remember, the last thing we were doing before we had this closure was we were working with motion and direction. We talked about distance and displacement. We talked about speed and velocity, which were pretty much the same thing except for the fact that velocity had direction. And we talked about acceleration. Those are the only things that I didn't go over in the little review units that we had in the previous week, just because it had been the most recent. So we just sort of recapped all the chemistry there, and we are starting fresh with physics. So we're going to start here with force. All right, so a force is a push or pull on an object. So an object being, touched, kicked, tugged upon, and any sort of change in motion is going to be caused by some sort of force. Okay, so the reason that an object moves is there's some sort of force that actually pushes or pulls on it. So if you look at these little pictures here, we've got the little guy with the weights. The reason the weights move is because he pushes upward on it, and the reason that this bowling pin falls is because the ball has been thrown down the lane, and then when it hits the bowling pin, it's a force that causes it to fall over. So we start talking about force. It's going to have units, of course. So it has a unit of a Newton, and that, of course, is after Isaac Newton. When we look at what a Newton actually is, because that's a nice, concise little just one single letter, N. But when you look at what it is, it's actually a kilogram meter per second squared. Now, we did meter per second already. That's when we had acceleration, because we were talking about the change in velocity over time. But now we're adding a kilogram to that, which means we've got to add in some sort of mass. So it's going to be some sort of mass and acceleration when we start talking about what a force is. But all we need to write down is just a Newton. Okay, so whenever you have a force or you see something and it has an N as a unit, then we know it is a Newton and that it was force. All right, so let's talk about the different types of forces that we have. There are frictional forces, and there is gravity. When you have friction, it means that the force is going to be because an object is touching it. Okay, so the first type that we might have would be static. So static friction would be like just the fact that the object is touching, okay, it's making contact. So when something walks, okay, each time that the foot makes contact, that would be static friction. Sliding friction would be that the object is being slid across the surface. So right now this paper is having sliding friction with the little table surface that I have here. Rolling friction would be what you would think about with like a ball or a wheel or like this roll of tape rolling across. Each time that it's making contact, okay, it's a different point of the table surface and a different point with that tape. So it's rolling. Something is, like we said, rolling across. And then fluid friction would mean that the object is in water and fluids around it, or in the air, and it's swimming, flying, falling. Okay, so you've got this fluid around it. Those are all types of friction. The other type of force is gravity. So gravity is always going to be acting downward towards the center of the earth. So that's what keeps us, not floating up into space. Gravity's pulling us down. Everything always has gravity acting upon it and pulling down. So when we start doing like these little diagrams in a minute, you're going to see that you're going to have a gravity force, and it's always going to be going down. When we start talking about gravity, we have to talk about its value. And if we're here on Earth, the number for gravity is 9.8 meters per second squared. So that tells us it is an acceleration, it's meters per second. But here on Earth, it is 9.8 meters per second squared. Now, this is a given value, and I've always talked about that sheet that they would give you on the final exam, and I have no idea what's happening with state testing. So maybe on the final exam, maybe we don't have one. I don't know. Things are changing every day if you've noticed what's going on in the world. So what I'm going to do is I'm going to actually upload for you that document so that you have access to the periodic table on that one side, and then all the formulas and stuff are on the other sheets, so that you'll have all those values and the equations that we're going to be doing in the next couple of weeks. But that's one of them that's there. It has gravity is 9.8 meters per second squared. All right, so let's look at a force diagram. So this is what a force diagram would look like, okay? And when we start doing force diagrams, remember I told you all diagrams were going to have this gravity, so that's what this F, G-R-A-V is for, force of gravity. But you also have to have a normal force. So it says when gravity acts on an object and pulls downward, but the object doesn't fall, it's because there's a normal force pushing up on the object. So this pen that I'm going to sit down right here on the table, okay? Gravity is pulling down or pushing down, pulling down. I can't show you underneath the table, but I'm trying to put my hand underneath there to show that it's pulling down, okay? But the pen's not falling through the table because the table is actually pushing back up with a normal force, equal but opposite. And most of you are familiar with Newton's laws, and that's the next set of notes that you're going to get. I always go with which is better to talk about. Do you talk about forces before you show Newton that deals with forces, or do you talk about Newton's laws that go right along with forces first? But I typically like to teach force and then teach the laws. I think it just kind of works better that way, but they can go hand in hand. Anyway, back to the diagram. If this little diagram shows the pen, the pushing down is the gravity and the pushing back up is norm. And that's why my pen doesn't move. Equal but opposite. It's got gravity and norm. All right, so then, when you start talking about whether or not the object's going to move, you have to talk about net force. So net force is the sum of all of the forces on the object, okay? So if this is a book sitting on a table, gravity is pushing down, okay? The table is pushing back up, and so the book's not moving up or down any, just like this paper. It's not moving up or down on the table. But if frictional is going to push to the left, now the sum net force is the 5 newtons that's being pushed leftward, because the 20 down and the 20 up are going to cancel each other out, okay? So the only force that matters is the force that was to the side. So that's why you see that the net force is 5 newtons left, okay? All right, so then balanced. Remember I talked about equal but opposite with that book first. So when all the forces on the object are balanced, the net force is 0 and it has no motion. So when my pen is sitting here, the force pushing down on it, 9.8, and the table pushing up, 9.8, is going to be equal. So therefore, the pen doesn't move, okay? It says balanced forces have equal sizes, but they're in opposite directions, okay? So when you're standing somewhere and gravity is pulling downward, okay, the floor pushing back upward on you, okay, you're not floating up or falling through the floor because those forces are balanced. Alrighty, so it says an object is moving with constant velocity, okay? So there's no change in speed or direction, then there's going to be no net force, okay? So if you're moving at a constant velocity, if you're falling through the air, if you're sliding along the floor, okay, and there's no change in your speed or direction, which would pretty much mean that you didn't have any forces playing against you, then you would have no net force there, okay? Otherwise, if you're rolling across the floor like a ball rolling across the floor, it eventually slows down and stops because there's friction that's going to slow it down. A net force, which are unbalanced, applies when an object will change its acceleration, which means it changes its speed. So that's typically what we see in real life because we have these frictional forces. So something's going to slow down because there's friction against it, okay? Whether it's fluid friction in the air, whether it's the rolling friction on the floor, okay, whatever that might be. Okay. So if the object is being pushed or pulled, the change in the motion is caused by the forces, and we already talked about that. So here, you know, you've got gravity pulling down on the book and the table pushing back up. And so here we have the friction between the table and the book surfaces, okay? You're pushing this way, but friction is pushing back across the book, okay? Think about if you've ever tried to roll something on a sidewalk, like maybe a wagon on the sidewalk. We've been doing a lot of that lately here at my house. So you're pulling, it's pulling easy on that nice paved surface, okay? If we want to roll the wagon down the road, if we want to roll the wagon down the driveway, so nice and easy because it's a flat surface. But if all of a sudden I were to take that wagon with my child in it and put it on some gravel, it's a whole lot harder, okay? So the frictional force there because of the surface that I'm rolling on, okay? So I'm not going to be able to speed down the road if all of a sudden I'm on a dirt road, okay? Because I've got a whole lot more friction, okay? So think about that. That's what's pushing back. It's going to slow or speed up. All right, so it says these forces here, they may have different sizes. They might be in the same direction. They could be in different directions, whatever it might be. Just depends on what we're looking at, okay? So now moving on to what I had mentioned before, your force diagrams, okay? So whatever object you're talking about, you're going to use a square to represent it. So even if it was, a ball, you get to use a square. If it's a book, you get to use a square. So we're not drawing these nice, pretty objects. We're just using a square, okay? So it says you're going to use arrows to represent the sizes, directions, and type of the forces, and the object is usually a box, okay? So here are the different types of forces that you could have. We already talked about gravity and norm, okay? If this object was moving over here to the right, it would be the force applied is to the right. So that's the fact that you're pushing it, pulling it. It's got, some sort of motor that's going to make it propel forward like a car. And then whatever is opposing it is going to come back the other side because that's the frictional force, okay, from the floor, the table, the road, whatever that might be, okay? Sometimes you don't have any left or right, and it's just gravity and norm, okay, that's going on it. So, here are some examples, okay. For this particular object, okay, you've got 2 pulling to the right, you've got 2 pulling to the left, maybe somebody's playing something like tug of war or something, okay, and if it's 2 this way and 2 that way, it's not going to move, okay, so this would have no motion because they're equal but opposite, okay. All right, over here, I've got 24 pulling down and only 12 pulling up. Well, the bigger number is down. So it's going to be moving down, but the actual force that it moves down is with 12 newtons because I had to subtract 24 and 12. Okay, no moving left or right, I only had forces going up and down. And last but not least here, I have 20 newtons pulling to the right and 5 coming back. So this one is definitely going to be moving to the right because the seniors versus the freshmen in this tug of war game, right? They've got more power. They're pulling with 20 newtons, and the freshmen are only pulling back with 5, so the difference there is 15 newtons, okay? So the freshmen are slowing down the seniors a little bit, but the seniors are still yanking right on. All right, so now let's draw some force diagram examples, okay? So your book bag is sitting on the floor of the classroom, I wish, but we're not there, so maybe it's sitting in your bedroom floor. All right, by the way, guys, I do miss you. I'm sorry we can't be together. I'm not going to say a whole lot about it because I get a little bit too emotional, but maybe we'll see each other before the year is over. All right, so your book bag is sitting on the floor of the classroom, so there's no motion. So definitely you have gravity. That is pushing down on your book bag, but because the book bag's not going through the floor, you also have the normal force that's pushing back up, okay? And you can write out grav and norm if you want to, but you will also see things like just Fn for normal and Fg for gravity, and even like FF for frictional force and FA for applied, okay? And that's perfectly fine. If you want to write out more like the words norm and grav, that's okay too. All right, now it says a ball rolling on the floor. Okay, so this does have motion. So here's my ball, okay. Because it's on a surface, it has gravity, of course, always pushing, and it's not flying back up into the air, so it's got the norm force. And since it's rolling, I'm going to say it's rolling over here to the right, so this is going to be its force applied. Okay, and actually I think I will write applied for that like that. But now, if I roll this ball across the floor, it's not going to roll forever, so it has friction, okay, that's actually playing back on it the other way, okay? So it'll roll further on a smooth surface, and this is what I was talking about like with the wagon. It rolls further on a smooth surface versus maybe like a carpeted or a rocky surface, but it's still going to have some sort of friction depending on, just whatever type of surface it is. All right, now, lastly, a ball being thrown straight up into the air. So if the ball is being thrown, okay, it's still here on Earth, you still have gravity, okay, but your force applied this time was forward, or not forward, but upward, okay? So your force applied is there. There is no norm force because it's not sitting on a surface. And so if you're not sitting on a surface, you don't have normal. All right, that's it for that. I will have some other practice for you that I'll go over and embed into the document, but that kind of gets you a basic understanding.